Yeah, hello guys. We are meeting once again. The topic for today is a dual cycle. So we are going to be starting off on that one. We are on a dual cycle. Now, maybe just a brief summary of how the diagram operates. We have from point 1 to point 2 where we have our compression stroke. This region between point 1 and point 2, that's our compression stroke. But between point 2 and point 3, that's our constant volume combustion. And then between point 3 and point 4, where our pressures are constant, we have the constant pressure combustion. But between points 4 and 5, we have our expansion stroke. Between point 5, which is the end of the expansion stroke, in between here we have our heat rejection or our exhaust. Now, one more important thing again about the dual cycle, as you can see, a dual cycle is basically a combination of an Otto cycle and a diesel cycle. So the term dual basically simply means that these are two cycles that have been integrated to operate as one component. Now, if you look here, we have our V2 and our V3, which are equal, and the only volume which is independent is our V4, V1, and V5, they are equal. In other words, you can see that even our pressures, they are extending up to cardinal number 5. Same applies to our volumes. They increase until cardinal 5. Now, let's go to the first question. On the first question, they want us to calculate the swept volume in cubic centimeters. So we are given a single cylinder engine working on a dual cycle principle. Here's a cylinder diameter of 78.5 millimeters. The stroke is given as 93.1. Clearance volume is 1/11 of the swept volume. Pressure at start of compression is given as 69 with a temperature of 40 degrees Celsius. Compression and expansion follows the law PV to the exponent of 1.33 equals to C. Our gas constant is given as 0.288. CP is given as 1.006, our CV 0.718. Heat added during constant, the heat added between cardinals 2 and 3, which is our constant volume combustion, is 0.19 kilojoules. Pressure at the start of the exhaust. The exhaust start from here. So the pressure at the start of exhaust, it is here, and then P, this point 1 becomes the end of heat rejection or the exhaust. So on A, let's solve the problem. They want us to calculate the swept volume. So let's solve that problem. We need our swept volume. Therefore, swept volume equals to pi d squared over 4 times our L, which is pi times our diameter is given as 78.5 divided by 1,000. I'm having 0.0785 squared over 4. Our stroke is said to be 93. So 93.1 divided by 1,000. 0.0931. So let's get our volume. Shift pi times 0.0785 squared over 4 times 0.0931. I'm getting 4.506 times 10 raised power of -4 cubic meters. But they want the answer to be in cubic centimeters. So we simply multiply by 10 the power of 6. So which becomes 450.587 cubic centimeters. So we have our swept volume, which is our A. Number B, they want all the volumes, temperatures, as well as the pressures. Now that because we have our swept volume, it is for us to get our CV, our clearance volume, which is our V2 or our V3. So we say CV, constant volume, equals to our V2 equals to our V3. How do we solve this one? It's our swept volume. It's our swept volume over our compression ratio minus 1. So it becomes 450.587 divided by 11. Remember, our clearance volume is said to be 1 over 11. So it's 1 over 11. So we are now saying 450.587 divided by 11. I'm getting a 40.962 cubic centimeters. So we have our V3, our V2, and our CV. So what is missing is to get our V1 and our V5. But V1 equals to V5, which is equal to swept volume plus our clearance volume, which is 450.587 plus 40.962. So let's see what are we getting. Plus 450.587 plus 40.962. I'm getting a 491.549 centimeter cubed. So we are fine. We have all our volumes, which is V1, V2, as well as our swept volume. So all our volumes are now there. The second part that we need to do is to get our pressures or our temperatures. So the easier thing that is there for us, because we are given the pressure at the start of compression, which is here, is for us to get our P2 from there. So we can say P1, V1, the exponent of n equals to P2, V2 to the exponent of n. So we can get our P2, which becomes P2 equals to P1 into V1 over our V2 to the exponent of our n. P1 is said to be 69. Our V1, we can use the compression ratio of the clearance. We can use the ratio of the clearance, so which becomes 11 plus 1, which gives us 12 to the exponent of 1.33. So we have 69 times 12 to the exponent of 1.33, which is I'm getting 1880 kilopascal. So I hope it's clear. Let's go to the second part. We can now look for T2, because our T1 was also given, which is 40 degrees Celsius, which we need to say, therefore T1 equals to 40 degrees Celsius plus 273. So 40 plus 273, which is we are getting 313 Kelvin. So we have our T1, so it's easy for us to get our T2. We can use our formula P1 V1 over our T1 equals to P2 V2 over our T2. Therefore, T2 equals to T1 into or rather, we are looking for T2, so T2 equals to T1 times P2 times V2 over P1 times V1. Yes, our T1 we said is 313, and then our P2 1880, and then our V2, did we calculate our V2? Yes, we have our V2, which you said it's what? 40.962, but it's centimeters, so we need to change it to meter cubed, so times 40.962 times 10 raised to the negative 6, divide by P1, which was said to be 69, and then our V1, it's 491.549 times 10 raised to the negative 6. I'm just converting them to meter cubed so that we get our answer with the correct position of our decimal. So let's get our answer: 313 times 1880 times 40.962 times 10 raised to the negative 6 over 69.491 times 491.549 times 10 raised to the negative 6. So I'm getting my T2 as 17.7 Kelvin. So we have our P2, we have our T2. The second step now becomes to get our T3. But if you check, this one took place, the energy that you are given, it occurred during the constant volume combustion. So from there, we can use our formula Q equals, or energy equals to MCV into T3 minus our T2. We can use this one because we have outlet and our inlet, but we don't have our mass, so we need to calculate our mass. How do we get it? So to get our mass, we can use our formula P1 V1 equals to MRT1. P1 is 69, V1, we said our V1 is 491, rather 0.549 times 10 to the power of negative 6 equals to M, our gas constant. It was given as 0.288 times 0.288 times, what's our T1? T1, we say it is 313. So from there, let's get our mass. So 69 times 491.549 times 10 raised to the negative 6, divide by 0.288 times 313. I'm getting my mass as 3.763 times 10 raised to the negative 4 kg. So we have our mass, we can substitute here, which is the 3.763 times 10, or rather we need to start off by putting our energy which is 0.19 equals to our energy which was given during the constant volume combustion. Our mass 3.763 times 10 raised to the negative 4. Our CV 0.718, it was given, into, we are looking for T3 minus T2, which we got as 710.7. So let's get our T3. So T3 equals to 0.19 divided by 3.763 times 10 raised power of negative 4 times 7, what else, times rather, not 7 is 0.718, which is our CV, plus 710.7. So we have 0.19 divided by 3.763 times 10 raised power of negative 3, rather negative 4 times our CV, which is 0.718 plus 710.7. I'm getting 1413.93 Kelvin. So we have T1, we have T2, we have T3. Now we can go for our pressures, because we have P1 and we have P2, we can get our P3. So we can use our formula, P2 V2 over T2 equals to P3 V3 over our T3. What is only missing here is our P3, because we have everything. Therefore, P3 equals to P2 V2 T3 over T2 times V3. So that is what is missing for now. But one exciting thing which we can also consider here, if we check on our cycle, CV is equal to V2 equals to V3. So we can just get rid of this one from our formula. So we just substitute P2. We said P2, we got it as our P2, we got 1880. So it's 1880 times T3, which is 1413.93, divided by T2, our T2, which is 710.7. So let's get our P3, which is 1880 times 1413.93 divided by 710.7. So I'm getting 3740.24 kilopascal. So we are sorted there. We have everything at our disposal. Don't forget, P3 is equal to P4. P3 is equal to P4. So we have P3 there as well as our P4. So what is missing? We have P4, we have P3. So we can look for our V4. I think that's the only volume which is not given. Yeah, that's the only volume which is not given. So yes, it has to be V1 equals to V5. Yeah, let us not make a mistake on this point, because V5 and the V4 are equal, but only V4 is independent. So for V4, we can now say V4 equals to V5 into P5 divided by P4 to the exponent of 1 over n. V5 is the one that we got here, where we added SV plus our clearance volume, which we got as 491.549 times 10 raised power of negative 6. P5, our P5, do we have our P5? Oh, yes, P5 was given. Where is the statement? The pressure at the start of exhaust. This is our start of the exhaust. So P5 is given as 330. That is the pressure at the start of exhaust. And then P4, we calculated it, we got as 3740.24. Our N, 1.33. So let's get our answer. So it's 491.549 times 10 raised to the negative 6 times 330 divided by 4, rather 3740.24 to the exponent of 1 divided by 1.33. So I'm getting my V4 as 7.92 times 10 raised to the negative 5 cubic meters. So you need to multiply it again by 10 to the power of 6, which becomes 79.213 centimeter cubed. So we have the other volume which was missing. So what else is missing there? Our T4 is missing. So our T4 is missing. So let's get our T4. So to get our T4, we can use P3V3 over T3 equals to P4V4 divided by our T4. We have everything except T4. So therefore, T4 equals to T3 times P4 times V4 divided by P3V3. So T3, our T3, we got it as 1413.93. Our P4 is 3740.24. Our V4, we just calculated it now, which is 7.92 times 10 to the power of negative 5 divided by P3. Our P3, which is 3740.24 times V3. Our V3, we say is the same thing as our clearance, which is 40.962 times 10 raised to the power of negative 6. So we can just get rid of this one because is it V4? Let me check something. Oh, because our P3 and our P4 are equal, so we can cancel these pressures. It's the same thing. So we have 1413.93 times 7.92 times 10 raised to the power of negative 5 divided by 40.962 times 10 raised to the power of negative 6. We are looking for a T4, so I'm getting my T4 as 33.8 Kelvin. So we now have almost all the temperatures with the exception of T5. So we need to get our T5. So which formula can we use? We can use our formula for T5. Can use our formula P4 V4 of rather P4 V4 yes over T4 equals to P5 V5 over our T5. So the only missing value there becomes T5. Therefore, T5 equals to T4 times P5 times 5 divided by P4 V times V4. T4, we have 2733.8. P5, it was given as 330. And then V5, 491.549 times 10 raised power of negative 6, which becomes 4.915 times 10 to the power of negative 4, divided by our P4, which we said is 37 40.24. And then our V4, we said it's 79, rather it's times 7.92 times 10 raised power of negative 5. So let's substitute then, see what are we getting. Okay, 27 and 33.8 times 330 times 4.915 times 10 power of negative 4 divided by 340.24 times 7.92 times 10 power of negative 5. I'm getting something like 1496 Kelvin. So we have all our temperatures, we have all our pressures at our disposal. The only thing which is missing now is to go to number C. Yes, we are now going to number C. So this was our number B, yes, the volume. So now we go to number C. On number C, they want us to calculate the compression ratio. So compression ratio, we can use V1, but RC equals to V1 divided by our clearance volume. We can use this ratio. Our V1, we got our V1 is 491.549 divided by our clearance volume. Our clearance volume, which we said it's our clearance volume, which is 40.962. 491.549 divided by 40.962. So I'm getting, my answer is 12:1. So that's my compression ratio. I'm getting a 12:1. So it now comes back to sum up that earlier on when we substituted, where I substituted 12 here, because I used the ratio of the clearance, which becomes 12:1. And then lastly, on number D, they want us to calculate heat received during combustion in joules per cycle. So for heat, we can use our formula. I'm running out of space there, so we can use Q equals to MCV into T3 minus T2 plus MCP into T4 minus our T3. So we have everything at our disposal. We already calculated our mass, which is this one, 3.763 times 10 to the power of negative 4. You substitute it here. Our CV is given 0.718. And then our T3, we have calculated it. We have our T3 we have our T3, which is 13.93, and then our T2, we have our T2, which is 17.7, and then plus our mass already have it, and then our CP is 1.00, is given 0.6, and then our T4, 27.33.8 minus our T3. So from there you get your answer. So this is how you deal when you have a question like this. A dual cycle, it's a very simple process, but you must remember that a dual cycle, it is made in such a way that it has 3 volumes, which is V2, V4, and V5. Those are the 3 volumes that we have. And then secondly, you must understand how the process operates. The moment they say to you, the pressure at the start of constant volume process, you must know that the pressure at the start of the volume, the constant volume combustion, is what? P2. If they say to you the pressure at the start of expansion stroke, you need to know that pressure at the start of expansion stroke is a P4. If they say to you the pressure at the start of compression stroke, which one is that one? Which is our P1. So once you understand that, it becomes easier to solve a problem, because they would do a lot of deliberate acts so as to confuse you. They will give you the energy transfer during the expansion stroke, the energy transfer which was lost during the heat rejection. So you can see during heat rejection we have what? It is between points what? 5 and what? And 1. Until we meet on the next time, enjoy your day, sharp guys.